Time does not function in the way that we have come to believe. This may seem like a somewhat esoteric statement, but our best equations that describe the universe are not compatible with how we view the concept. This is a Feynman diagram. These pictograms give a basic view of how subatomic particles interact. This diagram shows an energetic photon splitting and creating an electron and its antiparticle, a positron. You can see the positron is pointing backwards. This was Richard Feynman's way of reminding everyone of an uncomfortable fact. The equation that predicts this shows that antimatter travels backwards in time. Quantum mechanics is a large body of mathematics that makes very accurate predictions about the behavior of subatomic particles. That math, however, is entirely abstract. The equations are not mapped to any real-world intuition. With this framework, not even time is understood. Currently, we are stuck. Fundamental physics has not advanced since the 1970s, and I think our understanding of time is what needs to progress. It may be difficult to conceive, but our best equations definitively rule out the idea that a timeline represents physical reality. To understand why, we must go back to the origins of natural philosophy. We judge motion relative to our surroundings. You may feel like you are motionless, but you are on the surface of a planet that is turning on its axis, orbiting the sun, and the sun is orbiting the center of the galaxy at approximately 800,000 kilometers per hour. We are certainly not still, but if you're sitting down like I am now, you might feel still. This is because we judge our motion relative to our surroundings. The concept of relativity was first formalized by Galileo, and he demonstrated that it's hard to judge motion in any kind of objective sense. We can only judge it in a relative sense. This fact underpins Newtonian physics. An object in motion stays in motion unless acted on by an unbalanced force. In the 19th century, equations that describe the electromagnetic force were discovered, and it was found that these equations contradicted Galilean relativity. When an electric charge moves in relation to a magnetic field, there is an equation that describes what happens. But when a magnetic field moves in relation to an electric charge, that interaction is described by a different equation. Same relative motion, two different outcomes. This fact, despite contradicting Newtonian physics at the most fundamental level, went unexplained for decades until it was resolved by Albert Einstein. He accepted this fact and set about determining the consequences. His equations resolved this contradiction by redefining relativity. Galilean relativity is based on the notion of absolute space and time. Einstein's relativity is based on the notion of an absolute speed of light, which is invariant to any motion that the observer is experiencing. To achieve this, time had to be more flexible. As the velocity of an observer increases, time slows down, and from that perspective, the rest of the cosmos appears to speed up. Einstein called this time dilation, as when time slows down, it must be stretched across a larger length of the timeline. This allows us to make predictions about how things move, even though we all experience time differently. Space had to change as well. It had to bend in a way that we did not directly observe. We observe only the effect of this curvature. Einstein's equations correctly predict the gravitational lensing of light around the sun and other massive objects. We observe light bending around the sun. The math, however, tells us that light follows a straight line through curved spacetime. The equations predict gravity, and we observe objects accelerating towards massive objects. The math, however, does not describe gravity as a force, but as the natural result of the curvature of spacetime. This new description of the world did not match our perceptions. The equations work, however, so we accepted this description and accepted that the universe revealed its true self to us through the motion that these equations predict. Accepting Einstein's description requires a complete, total suspension of disbelief. and an adherence to the idea that not only can the math be used to make correct predictions, but that the story that accompanies the math is also correct. We learn to disregard our intuitive understanding of what we believe to be real. From a certain perspective, this seems reasonable. After all, the universe is under absolutely no obligation to make sense to us. However, what theory demanded of us did not end there. General relativity is often described as our best theory of gravity, but it is perhaps better to say that it describes how causes relate to effect. In this theory, nothing can travel faster than light, not even information. And it is this fact that maintains causality itself. Breaking the speed of light, theoretically, means total chaos. The behavior of subatomic particles described by quantum mechanics includes many bizarre occurrences, but perhaps the most troubling is the existence of phenomena that cannot be explained without accepting the idea that particles can communicate with each other instantaneously over any distance. The kind of information that can be transferred this way is very limited, and it almost seems finely tuned, as it does not seem to break causality. But it does leave unanswered questions. Where does this information limit come from? What separates so-called quantum information, which seems to break Einstein's speed limit, and classical information, which doesn't? 100 years later, these questions remain unanswered. There are many hypotheses, but it seems that the prevailing attitude is perhaps the human race has simply reached the limit at which we can understand the universe with familiar references. Perhaps there is nothing more fundamental to learn except raw mathematics, disconnected from any intuitive understanding. General relativity paints an interesting picture of the cosmos. This equation is completely unique. Neither space nor time are treated in the same fashion as they are in other equations. General relativity shows us that every particle has a unique continuity of time. Imagine two events happening at the same time. Three people see these events, but they are far enough away that light takes significant time to reach them. The first sees event A first and event B second. The second sees both at the same time, and the third sees event A followed by event B. A limited speed of light means that they will not agree on which events might be considered simultaneous. General relativity takes this picture to a whole new level. Not only can they simply not agree on what events are simultaneous, the very concept of simultaneous events becomes meaningless due to the geometry of spacetime. Simultaneous events, when time is treated as a dimension, requires time coordinates that can be compared across spacetime. But the geometry of this equation simply does not allow for that. The curvature of spacetime shows that every particle has a unique timeline. General relativity can be interpreted as presenting a kind of multiverse, where every particle has its own timeline and there's a set of rules that ensure that these separate timelines can interact with each other. As far-fetched as that might seem, the study of subatomic particles revealed behavior that could not be explained with any kind of traditional logic. Quantum mechanics represents some of the most complicated math that we've ever created, yet it is entirely abstract. It doesn't just ask us to readjust our intuition. In some ways, it requires us to abandon it. Even time, a fundamental parameter of any theory, does not make sense in this realm. Paul Dirac was the physicist who successfully combined quantum mechanics with special relativity. His equation did a strange thing. It predicted the existence of particles that have negative energy. Dirac insisted that these solutions should not be ignored. He argued that they represented a fundamentally different kind of matter, antimatter. And this insistence paid off when antimatter was discovered soon after. Antimatter has never been properly defined. Mathematically, the relationship between matter particles and their antimatter counterparts is symmetric, and it's only a matter of convention that the common particles are labeled matter. The Dirac equation was reinterpreted by the physicists Richard Feynman and Ernst Stuckelberg. This interpretation took the math even more literally than Dirac. The mathematics describes antimatter as traveling backwards in time. While this interpretation does not make logical sense, it makes understanding the mathematics easier, and Feynman used the idea in his famous diagrams. Energy has a frequency, and negative frequency requires negative time. So this is a literal interpretation, which is not meant to be taken literally. Currently, our equations exceed our ability to understand them, and this fact represents the biggest gap in physics today. The remainder of this video describes my attempt to solve this puzzle. We are always aware of the passage of time, but time and motion are inseparable. The wind impacts our skin, and we become aware of the motion of the air. We hear the sounds around us as the vibrations in the air impact our eardrums. Light impacts our retinas, and we see the world around us. The internal motion of our minds create memories and connect our senses to our conscious experiences. So we never experience time without motion, yet we treat them as separate. For the universe to exist, cause and effect must follow consistent rules. Temporal ordering, which is the idea that cause and effect is a chain that can be described along a consistent, coordinated timeline, is how time is usually imagined. But if we consider that motion and time do not exist separately, time can also be thought of as a user-defined parameter, a value that you assign to a record of what has happened, regardless of the underlying physics. The first statement is implying that coordinate time is a fundamental, universal property. The latter is a description of how we use the concept of coordinate time to describe the world and to solve problems. It may sound surprising, but causal ordering can be achieved without coordinate time. General relativity does not use time to maintain causality. Time is simply one of 4 dimensions, albeit with different geometry. Instead, causal ordering is achieved using the equivalence principle. The speed of light functions as an invariant but dynamic budget of motion. In this theory, all objects move at the speed of light, but much of that motion becomes lost in the curvature of spacetime. The speed of light represents not just a universal speed limit, but an invariant unit of motion that appears dynamic because spacetime is curved. Although the quantum mechanics employs temporal ordering to maintain causality, much of how the theory functions is through similar constraints. The Planck relation, which represents the discovery of quantum mechanics, describes photons as being constrained by the speed of light and Planck's constant. The concept of action is extremely important in physics. The unit value that Planck's constant has covers every basic unit of measurement. It represents all forms of motion combined into a single unit type, a quanta of action. General relativity successfully describes causality using the equivalence principle, but we can build on this idea by finding the appropriate constraints. The Dirac equation functions by constraining mass, phase, and momentum, in addition to the speed of light and Planck's constant. Using it, I have created this first iteration of a synchronicity constraint, the Dirac sigma. It functions as both a record of motion and as a universally invariant but dynamic budget of action. All particles are constrained by this budget. A photon has no mass. Because of this, it uses its entire budget to move. Its frequency represents its budget density. Dirac matter, on the other hand, can use its budget internally. It occupies space, which is 3-dimensional, and has an internal phase that emerges as an electromagnetic charge and as the parameter that we call proper time. When the particle gains momentum, both the budget allocated to occupying space and its proper time contracts, as the momentum that has been gained requires a portion of the particle's invariant budget. Time dilation is not real in this picture, as that is what occurs when contracted proper time must be stretched to fit coordinate time. Time contraction occurs, time dilation does not. Symmetric contractions in length and proper time result in an invariant observed speed of light without curved spacetime. Objects simply exist in 3 dimensions in this picture. The 3 axes have a small internal degree of freedom as they are not perfectly straight, but divergence away from the axes is limited by Planck's constant. The invariant constraint determines the allowed configurations of the particle, including the relationship between its momentum, its length, and its proper time. The negative frequency solutions of the Dirac equation are easily interpreted in this picture. Frequency is just the internal cycle of the particle. The equations of motion are time-symmetric. So if two identical particles are evolving in time, one backwards, one forward, they will look identical, outside of interactions where the negative or positive frequency might have influence. The Dirac equation disproves the existence of a timeline. As if one were real, antimatter would disappear into the past. In addition to resolving the time paradoxes that emerge from quantum mechanics, many of its axioms emerge naturally when we base it around this synchronicity constraint. Interactions do not occur because of temporal ordering, but because of synchronicity. The constraint cycles, and when identical or symmetric particles have matching internal phase, matching sigma, they entangle when they interact. This entanglement can continue across any distance of space as long as the synchronicity constraint is not broken. If we convert these parameters into space-time coordinates, we can see that from the perspective of coordinate time, this single quantum state will remain intact and quantum information can be shared across it, as long as these space and time coordinates change at a symmetric rate. In orthodox physics, this is called a Bell violation, or non-locality. Perfect synchronization is rare, however. Most interactions between matter particles are periodic. When two particles have mismatched sigma, they can still interact. Their phases may occasionally align, resulting in a point-like interaction. This describes the Heisenberg cut. Perfect synchronization, which allows for the non-local sharing of quantum information, requires perfectly matching values of sigma. But momentum can only be exchanged when particles have mismatched sigma, as an imbalance of momentum is required for an exchange to occur. It is also the origin of both wave-particle duality and probabilities, as periodic synchronization is not guaranteed. If no point of synchronization occurs, the particles will tunnel through each other. An effective method of calculating these interactions is with the path integral. The combination of wave-like nature and periodic synchronization can give the appearance of many paths being possible. This is the origin of the superposition principle. Probabilities reflect the concentration of paths near stationary phase. So when probabilities are coarse-grained at the classical scale, the principle of stationary action emerges. All of these principles exist in standard quantum mechanics, but they are assumed, postulated, not derived. From equivalent time theory, they emerge with intuitive, causal explanations. This space-time budget is the same everywhere, at least at the cosmologically local level, and this has created the illusion of a timeline, as every particle is limited by this same, identical parameter. This illusion only becomes apparent when the budget density scale of the system being measured exceeds a certain limit. Albert Einstein's description of spacetime requires a complete suspension of disbelief. You must ignore your own perceptions of space and time, and have faith that both the equations and its underlying ontology are correct. But we do not perceive time as a shared dimension that we are moving through. We perceive it as an instantaneous moment. The past changed into the present, and the future is what the present will change into. Time is a product of many interacting phenomena, and due to the symmetry of these relationships, we have misunderstood the hierarchy on which they are built. Time does not create rhythm. Rhythm creates time. Thank you.